Okay, let's talk about blood pressure. And for this, I would strongly recommend that you get a piece of paper and a pencil or something to write with, because blood pressure and discussing and understanding the factors that determine blood pressure really require just algebra. And it's simple algebra. It's not hard algebra, but it's algebra. So if you can't keep the factors straight in your head, it often really helps out if you just write it out as we go along. So blood pressure, what is a normal blood pressure? So a normal blood pressure is about 130/80 or below. Hypertension, which is a high blood pressure, is 140/90 or above. And there are different mechanisms that increase your blood pressure. And as we're talking about this, realize that a lot of these mechanisms are very adaptive, right? And so if you are losing blood, then your body needs to regulate your blood pressure in order to maintain the flow, maintain the forward flow. And so it does that through the systems of regulation, like the renin-angiotensin system, the sympathetic nervous system. And those work mostly by constricting or vasoconstricting the blood vessels. Now, there are a couple other ways that they work too, but right now we're just going to go through the math. So here is the big algebraic equation. So blood pressure equals cardiac output times peripheral resistance. So this is what I'm talking about. So blood pressure equals cardiac output times peripheral resistance. And then we're going to break down both of those components, cardiac output and peripheral resistance, because what do I mean by that? So let's start with cardiac output. This is like an algebraic equation inside an algebraic equation inside an algebraic equation. Okay, so cardiac output equals, so we're only talking about the green box, cardiac output equals heart rate times stroke volume. What does that mean? So stroke or heart rate is pretty self-explanatory, right? It's just how fast your heart is beating. So let's just start there. If I say that someone got scared and their heart rate increased by 10 beats, what is going to happen to their blood pressure? Well, we can plug in the equation, right? So increase of heart rate, if we do our algebra, that increases the cardiac output and that increases the blood pressure. Simple as that. What does stroke volume mean? Okay, well, stroke volume is basically the ratio of the blood that is squeezed out of the heart during systole, because the heart relaxes during diastole and it fills with blood. And whenever it squeezes during systole, not all of that blood is ejected. And so stroke volume is like the percentage of blood that is actually ejected. And when you have your sympathetic nervous system working on your heart, one of the things that it works on is an increase in contractility. And so what does that mean? It almost makes it more like a rubber band. It stretches it out so it can shoot farther. And so basically the same thing happens to your cardiac muscle cells, stretches it out so it can shoot farther. And so whenever your sympathetic nervous system is acting on your heart to increase the contractility, it increases the stroke volume, which increases the cardiac output, which increases the blood pressure. Okay. So Max is found to have high blood pressure, and the doctor recommends a low sodium diet. Why? So this is related to that fluid follows salt, right? In addition to the sympathetic nervous system working on your stroke volume, the other thing that works on your stroke volume is just having more volume in the system. And so if I eat a lot of salty food or whatever, the water is going to follow the sodium, right? And so I'm going to retain fluid. And that's going to increase my volume, which that will impact the stroke volume, which impacts the cardiac output, which impacts the blood pressure. And all of those are going to be elevated. And so the reason that the doctor recommends a low sodium diet is to do the opposite, to decrease the stroke volume, to decrease the cardiac output, to decrease the blood pressure. Okay, so peripheral resistance is a little bit trickier because this equation looks a little scarier, right? But it's not. So peripheral resistance is basically the resistance to blood flow. Okay, what does that depend on? Well, 8 times the length of the vessel times the viscosity of blood over pi radius to the 4th. So let's define some of these terms, right? So the length of the vessel, that's self-explanatory. There aren't very many situations or scenarios where you're going to have an increase in the length of your vessel, right? And so hypothetically, whenever you're seeing questions, the only reason why you would have like a really dramatic length increase in your blood vessel and your vasculature is 1, if you gained a ton of weight, 2, if you had some kind of tumor that was triggering the growth, angiogenesis, triggering growth of blood vessels, and you have this like maybe ball of blood vessels somewhere. But the main physiologic reason why you would increase the length would be due to pregnancy, right? Because now you have a whole nother system added onto your own blood vessel system. And so that's really going to probably be the only scenario where we increase our length. Viscosity of blood. You guys know what viscosity is. It's like the thickness, right? And so think of honey as being more viscous than water. And so what would make your blood more like honey than water? Well, being dehydrated, for one. There are certain scenarios where you increase your red blood cell count, and so that would make it more viscous. If you have a whole lot of triglycerides like fat, and if you're mobilizing energy stores, that might make it more viscous, right? Because the solution is thicker. And then the radius of the blood vessel, this is, just the radius. And so what affects this? Well, this is totally affected by your autonomic nervous system. Sympathetic nervous system makes the radius shrink, and parasympathetic nervous system makes it relax, makes it bigger, right? And because we are making the radius, dividing by the radius to the 4th, the radius is going to have the biggest impact on your blood vessel or your blood pressure. So exposure to extreme temperatures can impact blood flow. Heat can lead to dehydration, which results in hemoconcentration. How would this affect blood pressure? Well, right now we're just talking about the viscosity of blood. And as we go through these, keep it simple. I know that there's going to be a complex dynamic that eventually happens, but for now we're just learning the algebra. So keep it simple. We're only talking about dehydration, which leads to hemoconcentration, which means that we've just increased our viscosity of our blood, right? And so you can see this is the letter for viscosity, and that is in the numerator. So if we increase viscosity, everything else stays the same. We have increased resistance. Okay, so if we increase resistance, then we have increased blood pressure. That should make sense at this point. If not, rewind and listen again. So next case, and I know that there are 2 case 5s, but this is case 6. So the sympathetic nervous system is activated. That causes the blood vessel to constrict to half of the original radius. So we went from 2 millimeters to 1 millimeter. how would the change in the radius affect the resistance and blood flow? So for this particular equation, pause the video and see if you can plug it in. And for the most part, like most of these are going to be constant. And so you could simplify this equation by just saying peripheral resistance equals 1 over r to the 4th. Because pi is, constant. The viscosity is mostly constant. The length is mostly constant unless you're pregnant or you have a huge pathological tumor. So if we simplify this to 1 over r to the 4th, what happens to our resistance if we decrease it by half? And all you have to do is plug in the 2 right here, do the equation, and plug in the 1 right there and do the equation. And go ahead and take the time to do that. Pause the video if you need to. So when we work out the equation, here's what we get. Plugging into the 2, our peripheral resistance equals this. And then when we put a 1 in there, if we decrease it by half, then our peripheral resistance equals 1. And so if we divide 1 over this, then we have just changed our peripheral resistance by a factor of 16. So that is why the peripheral resistance really has, or the radius has the hugest impact on peripheral resistance because it's in the denominator to the 4th, because we just decreased our radius by half, right, with vasoconstriction, which is mediated by the sympathetic nervous system. So fight or flight, constrict, the radius is smaller by half, but that increased our resistance by a factor of 16, which means it's also going to increase our blood pressure by that amount too. So here are the equations put together. Cardiac output equals heart rate times stroke volume. Peripheral resistance equals 8 times the length times the viscosity over pi r to the 4th. So try to do this in your head or on your piece of paper. Try to figure this out. And for this particular equation, I want you to assume that all of the changes equal each other. So we're only looking at basically net up, net down, net up, net down. Forget what I just said about the radius actually, playing the biggest role. So for this one, just, what is the vector of direction? So during pregnancy, a woman's blood plasma volume increases by 50%. This is true. So the volume just increased. Which one did we increase? Stroke volume, right? This results in a relative dilution of the blood. Think of what we just affected and in which direction. Additional blood vessels are formed to make the placenta. Now, which factor am I talking about? In which direction? And numerous hormones result in profound dilation of blood vessels throughout the body. So what is the net change? How would these changes affect a pregnant woman's blood pressure? Take a couple of minutes, work it out, see if you can find the net effect. So the answer is it doesn't. The net effect is 0 because we just increased the plasma volume, which we increased that, which would increase the blood pressure, right? We diluted the blood, which decreases the viscosity, which decreases the blood pressure. So that's a net effect of 0. Additional blood vessels are formed to make the placenta. So we increase the length, which increases the blood pressure. So that's a net effect of increasing. And numerous hormones result in profound dilation of blood vessels throughout the body. What did we just do? We increased the radius because vasodilation means that the blood vessels relax, right? And the radius increases, which means the peripheral resistance decreases because we are actually dividing by the radius, right? So if it's in the denominator and we increase it, the peripheral resistance is going to decrease, which means the blood pressure decreases. And so that's a net effect of 0. And so it is pathologic for a pregnant woman to have hypertension, even though her body is going through these extreme changes in so many different directions, the net effect should still be nothing. And so that's why whenever we talk about reproductive health and maternal mortality, remember this, like it's supposed to be a net 0. And that's why it's pathologic if her blood pressure is high. So if you don't understand that, go through it again, take the time to figure it out because you really just have to follow the algebra. So let's talk about blood pressure regulation.